Right, welcome back. So, we're changing a bit gears today. We started on Monday and also on Tuesday. We discussed the Kitaev chain as an example for an SPT phase, which is fermionic. So essentially, once you write this model in terms of fermions, depending on the parameters, there is a regime where you have fermionic edge states, where you have a bulk topologically invariant, and that's topological phase. And then there is another phase, which is where the system is trivial, there are no edge states. The symmetry ultimately was, the important symmetry in this problem was the Z2 symmetry. We discussed the symmetry fractionalization, and the fractionalization had this fermionic representation. Then yesterday, we switched from fermions to bosons in this more general sense. So we switched to a spin-1 chain and discussed an SPT phase and interacting SPT phase for this spin chain, the AKLT phase. And we also discussed the symmetry fractionalization for that. So for both of these situations, we had, as usual for SPTs, a gapped ground state, so gapped from the many-body spectrum, and we had edge states in the presence of open boundary conditions. Now, I originally had planned to do some more details about spin chains, but I will postpone them maybe towards the end of the lecture, depending on how far we get. And I thought it's worthwhile to now switch to topological order. And I would like to discuss today the toric code. So, maybe let's start writing things down, and then I'll explain to you what the connection is to what we did in lecture 1. So the title of this section is the 2D transverse field Ising model. Z2 gauge theories. And toric code. So remember that the first lecture, the first and the second lecture, we started from the one-dimensional transverse field Ising model. And maybe I should draw this also. Let's see. So remember, in the first lecture, we had a 1D transverse field, 1D transverse field Ising. With the phase diagram, it looked like so. We had J over lambda, which was the interaction, which was the transverse field. Here we had spontaneous, so in terms of sigmas, we had here spontaneous symmetry breaking. We had here disordered space, disordered in the sense of not ordered, or quantum for a magnet. We also had dual variables called mu. There it was reversed. This was the symmetry broken phase. This was the disordered phase. And then we had the zetas. Actually, the zetas constructed from the sigma. Somewhat makes it important. In this notation, this was the topological, and this one was the trivial phase. So we introduced the original degrees of freedom, which were spin. We introduced the dual degrees of freedom, and we showed that the model essentially maps back to itself, other than that J and lambda are extinct, modulo some effects at the boundary. And we also showed that we can write the whole model in terms of fermions, and we can actually solve it in terms of fermions. And then this phase here corresponds to the spontaneous symmetry phase, corresponds to the topological phase, and the triple phase. Let me emphasize again, in this language, there is no notion of symmetry breaking. If you wish, out of the zetas, you can construct the order parameter, but then it's very non-local in terms of zetas, so it's not a local order parameter. So it's not a symmetry breaking. Today, we do the same thing in 2D. 2D, same thing. But what we will see is actually that, so in terms of sigmas, there is still such a phase condition at some order 1. So this is still true for today, so in red is today, so again there is disorder. And there is symmetry breaking. But then, there's also, let me just check this briefly. We will also map it back to mu's, not to the zetas, but to the mu's. And the disordered phase corresponds to the trivial phase in terms of topological order, and this one has topological order. So this is again in terms of mu's, topological order. So the idea behind doing all of this transfer easing business is, first of all, it's a super easy model for discussion of symmetry breaking, etc. But to also show you that these concepts of both SPT and topological order are in a non-local way related to simple SSP physics. Yes.
Just about this simple one-dimensional example you've shown with Eisen. So it seems that by switching sigma to gamma, we completely reverse our model.
Which one is gamma?
Yes. So
mu? Zeta?
Yes, exactly. So then getting to the next variables. Yes.
Yeah.
We completely reversed our model, and of course, so disordered one is in another, but after all, one of these phases is, so it seems that the phases are completely equivalent after this transition.
Well, as I said, right, so this, one has to be a bit careful with boundary conditions, etc.
Yes.
Up to that.
But after all, disorder in sigma state is trivial. And so what is actually the difference between writing Hamiltonian in terms of sigma and writing Hamiltonians in terms of second variable?
So, not sure what you mean by different. I mean, the logic is to, these guys are indeed the disorder operators, these are the order operators.
Yes.
You map one on the other. Of course, as we discussed in terms of counting ground states, this is only one ground state, these are two, etc. So this is coming from all of these subtleties. But other than that, it shows you, the idea of Cramer-Sonnier originally maybe for 2D finite temperature is to find the critical point and to see that there is a duality between the phases. Not sure what is your question?
I meant that it seems that after this transformation, you completely you transform your Hamiltonian to exactly the same.
Yes.
But we switch parameters.
Yes, exactly.
Right?
Yeah. In the
but you have topological and trivial states.
Here now, in terms of zetas.
Yes, but it seems that they should be in some sense the same.
Okay. Well, you see that I put an arrow from sigma to zeta.
Yes.
I could also start from the model in terms of mu and then create some zeta twiddles out of the mu's. And of course, then it would be reversed.
Okay,
right?
so this is topological in terms of sigma.
Yeah,
I would say. Okay.
and that's also, so the mapping from sigma to zeta at finite, for open boundary conditions is exact. There is nothing more. I mean, I showed you everything. There was no nothing under the rug. If you wanted to do the same thing from mu's, you have to be, well, you get something different, right? I mean, because going from here to here has some subtleties at the boundary. So therefore also, here for example, the topological phase has a twofold ground state degeneracy because of the edge state. That's consistent with the twofold degeneracy of the SSP.
Okay.
Right? But in open boundary conditions. But here, yeah, so this would be a slightly different one. So the usual mu chain with open boundary conditions has the twofold degeneracy here and only one fold here. And then the zeta twiddle would have the reverse semi. Yeah. Okay, so we're doing the 2D transfer model, but we're actually starting theoretically. I reverse engineered the story. So I start to introduce the Z2 lattice gauge theory, and then I will show that the Z2 lattice gauge theory is actually the dual theory to the transfer sweep easing model. So I should emphasize that here, this is transfer sweep easing model. This is transfer sweep easing model. If I start in terms of sigmas, I have here the transfer sweep easing model, but it doesn't map back to the same model with opposite parameters. It maps to something completely different, namely to the Z2 gauge theory. Yeah, so this is work from Wegner from the mid, maybe around 1970, to show that when you do this Kramers-Thurmanier duality in 2 dimensions, instead of going from the model to itself, you go from the model to a different theory. So there's no even hope for such duality. Okay. But again, I do this reversely. I start here and show you that this is this. But before starting here, since I don't know if everybody knows what the Z2 gauge theory is, I first introduce what it is. Maybe I should write, to be concrete, Z2 lattice gauge theory. So you probably all heard about Ken Wilson, and you know that there is lattice gauge theory in principle, that people do this to whatever, study QCD or so. So this is essentially taking a gauge theory and putting it onto the lattice. And the simplest gauge theory that there is, I would say, is Z2. The problem is with Z2, I don't know, my personal intuition is better for U1 than for Z2. I somehow have a feeling for charges. I feel that, but not so much for Z2, but we can make analogies and learn from that. Okay, so this is I'm going to introduce the pure lattice gauge theory without any matter fields. So think of electrodynamics, then the Hamiltonian would be E squared plus B squared. Here the Hamiltonian is the following. H equals minus J. I introduce this in terms of new variables, as I already said. Sum of all bonds, mu bond X, minus lambda, sum of all plaquettes, B of a given plaquette. And B of a given plaquette is nothing but the product of all bonds which are adjacent to this plaquette. This is a del. Mu Z bond. Let me illustrate this graphically. Actually, why did I write it in blue? I don't know, but so we have a square lattice, let's say. We can do this actually in any lattice, but let's do a square lattice for simplicity. The degrees of freedom live on the bonds of the lattice. Also, that is a choice. I could have drawn a lattice which is 45 degrees rotated and then open the vertices. But it makes sense to put them on the bonds. So each of these squares here is a two-dimensional Hilbert space. So it continues, huh? And we have two types of operators. One operator, so this is Hamiltonian. One operator is just mu bx, right? So let's draw this in orange. So here, just mu bx. Just living here. So this is the J term. Just x in this one group. Or spin, or whatever you want to call it. Yeah, so I said two-dimensional Hilbert space. Right? 2D local Hilbert space. And then there is something a bit more crazy. This is this plaquette there. This is this line here. And that's the product of mu z at this bond times mu z at this bond times mu z at this bond times mu z at this bond. By the way, maybe I should ask, who knows about Tory code already? These are like around about 10% maybe. Thank you. Okay. So, why do we call this a lattice gauge theory? First of all, an important thing to introduce here is something that is present in the gauge theories, which is a Gauss constraint. Sorry, I'm not sure why I started in blue. Gauss constraint. So there is an operator that we define that is QR, product of all B's adjacent to a certain point. So R, so B denotes a bond on the lattice, R denotes a vertex on the lattice. So we have here UX R, and the constraint is QR equals 1. I think we take 1 in this case, yes.
Or not mu x r, but mu x b?
No, here?
Yes.
Oh, yeah. Red. Yeah, so this is my Q operator. And this Q operator, let's put here one more box. This guy is UX, 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 UX. Yeah, and so sometimes they are called star operator and packet operator. Okay.
R is the node.
Say again, please?
R is a node with this lattice.
Yeah, vertex. Yeah, I know it. Yeah. So why is this called lattice gauge theory? So first of all, what is a gauge theory? It's something where you have, I think of it from the perspective of field theory. So you have a field psi, maybe in space-time. And a global symmetry is something where you just roll it, let's say, by a phase. And the local symmetry is when you do this. Phase is time dependent and time and space dependent. And maybe at the same time you have to do something like A goes to A minus gradient phi. Do you agree this is phase? This is the gauge theory. So when you have a gauge theory, you have local, you have in this case a U1 rotation locally in each space-time. That means that you have local conservation laws. Yeah? I mean, you have an extensive number of conservation laws because you have an extensive number of them. That's essentially what's happening here. So we have this object here, this Q, which ultimately is conserved because this theory has an extensive number of conservation laws. Namely, we can flip the Z's. The Q operator actually generates it itself. So it flips Z's around. Okay, so maybe I should say what's a bit confusing here is that this here is sort of the A. We're discussing so far only the A, and the Q's themselves are ultimately the conserved quantities. So each Q is a conserved quantity corresponding to the local conservation laws of such a symmetry. To see that each Q is conserved, let's just look at the Hamiltonian and see that the Q commutes with this Hamiltonian. The Q obviously commutes with the mu B axis, because the Q is composed out of other mu B axes. And then the Q commutes with the B, because when they are not next to each other, they don't share any Hilbert space, there's nothing that could be not commuting. When they are overlapping, let's say we look at this star here, then we have, and we want to bring the Q across a B, we get a minus sign from bringing this mu x across this mu z. We get another minus sign from bringing this mu x across this mu z, so we get two minus signs, and in total this is no minus sign. Okay? So the fact that we actually can impose such a Gauss constraint is related to the fact that this is a The toric code is the same theory. It's the same theory, but with a soft Gauss constraint. Soft Gauss constraint. There we have just an extra term in the Hamiltonian, which is minus h sum over all r qr. So instead of enforcing this exactly, in the toric code it's energetically enforced. If h is positive, we want to have the qr's to be 1. Otherwise it pay energy. So if you wish, the Z2 gauge theory can be obtained from the toric code by taking h to infinity. Now, I explained a little bit that the gauge theory is something which has like an extended number of observation laws, but maybe it's still not quite obvious why this is a Z2 gauge theory. So what do you typically expect in a gauge theory? As I said, for the pure gauge theory, we have a Hamiltonian which is E squared plus B squared U1. Actually, it's a little bit more complicated. If you have U1, if I just do a little, it helps me at least to think a little bit about the U1 that is gauge theory. What do we have there? So we would expect for H something like E squared plus B squared, right? That's what we expect. In fact, the Hamiltonian for the U1 that is gauge theory is it has to be a compact QED. The Hamiltonian in that case is sum over all bonds, and then you have here minus I d phi bond squared with a prefactor which we call minus j here, minus lambda sum over all packets cosine of the flux. Lambda. This is a side remark, that's why I'm writing it here. You don't necessarily need to take notes on this. But I feel it's helping you think about gauge theories. So this is Polyakov's work, maybe also in the late 70s or something. What do we have here? The U1 case, again, I think the U1 case is easier to think about. U1, you have a lattice, maybe you have electrons hopping around the lattice. How do you couple them to the gauge field? You do pi L substitution, right? Yes?
What is phi B and phi like that again?
Yeah, I will do it. I need to get there in a second. Sorry, I'm not there yet. So imagine you have electrons hopping around the lattice. You will have C dagger, I, Cj, right? And to make this gauge invariant, you have to put here integral dx from xi to xj A. Right. You agree that this is the way to make it gauge invariant. This is called pi L substitution. Usually when you do this, oftentimes in convex matter we do this, but then we don't treat this as a dynamical variable. Here we want to study gauge fluctuations. So then you take this guy here, which lives on the bond ij, make it a dynamical variable, you call it phi on the bond ij. Question? So the phi's here, they live on the bonds. On each bond, we have an e to the I phi. Yeah? So in the case of U1, you have an e to the I phi on each bond. I phi on each bond. Yeah? Then, in the U1 case, this here is nothing but e to the I integral, contour integral around a given packet A of L, right? Which is nothing but classical Hermitian conjugate plus complex conjugate of Hermitian conjugate, which is nothing but e to the I, whatever, like phi 1 plus phi 2 minus phi 3 minus phi 4 or something, go around it. You agree that this here is cosine of the physical flux, I guess, right? right? The flux that you encode in such a plaquette is what you get by taking the contour integral around this, right? And therefore this here is cosine of the physical flux. When you expand this cosine close to 0, you get b squared. Agreed? So that's what the U1 version looks like. Now what's this guy here? This here is the guy which gives you dynamics to each of the phi's, right? Because if you think of phi now, instead of thinking of phi as really what it is, the integral over the vector potential, you think of phi as just phase. You have a rotor on each of these links, and or you can think of a floating superconducting granule. It's a phase that is, it's just described by a rotor. To which it's a particle. On each side we have the Hilbert space of a particle living on a ring. And what's the kinetic part for a particle living on a ring? Well, it's just p squared. This is p squared. Agreed? Why is this in this Hamiltonian for the U1? So if you think of going from here, from the Hamiltonian to the Lagrangian, what do you get out of the p squared part of the Hamiltonian? You get something like v squared, right? So you get in Lagrangian, this term here will give you minus j or plus j v squared. Right? Something like v squared. But that's nothing but minus j or plus j. Essentially what this is at a given side is something like, we call this A, this was our vector potential. Phi is essentially A. So it's something like A dot squared. So what I'm trying to say is that minus I d phi becomes something like A dot. But A dot is, at least in a given gauge, is the electric field. So this is essentially E squared, and this is essentially B squared plus x plus x. Okay. This is something like the momentum. This is the momentum operator for a particle on a ring. When you do path integral and represent this thing in the Lagrangian, you get the path integral, you get the action, and there will be classical Lagrangian. And there will be a v, velocity. Velocity is phi dot, or a dot. I'm jumping between, this is very informal, but I'm jumping between the notation of phi and a, just to give you an idea of where this all comes from. So this becomes actually phi dot, but that's nothing but a dot. And that's nothing but a dot. So essentially what this describes is on each link, the phi dot here describes the E field in this direction, the phi dot here describes the E field in this direction. Yeah? And then we have that. Okay, so this is about U1 gauge theory. And that's the connection, yeah? So we have so in here, this guy is obviously the same as this one. We now restrict ourselves to a Hilbert space which is smaller. We don't allow the full tower of states that you have on a rotor. We allow ourselves only 2 states. And these 2 states are going to be corresponding essentially to phi equals 0 and pi. And then this b is just, so you see when this is phi equals 0 pi, you still go around, then the cosine here of course also can be cosine of either 0 or pi. And this is the b term, which essentially takes the product. All of these mu's is nothing but taking the line integral under the assumption that these phi's can only be 0 or pi. On the other hand, there is this fellow, and now this is where my sort of intuition starts to become worse. But this guy is what's called the E term in the context of Z2 gauge theory. By analogy, because this guy does not commute with this one, so it creates dynamics similarly to this guy does not commute with this one. Okay? I mean, this was informal, but I thought this is maybe helpful to get a feeling for lattice gauge theories. All right. So that's the part that you should retain. That's the part that was sort of some background information. Yes. So okay. So maybe since we're anyway speaking about the general connections of this model with other models, So I introduced this as a essentially statistical mechanics problem. In fact, I'm going to show you, as I told you, is that this theory, the blue theory, is nothing but the transfer speed Ising model in 2 dimensions in disguise. As a non-local duality transformation which brings the blue theory to the transfer speed Ising model. So this is related to fundamental statistical mechanics. That's how it was introduced. I then made a connection to high energy physics, discussing how the connection to lattice gauge theories, let's say U1 gauge theories. The simplest lattice gauge theory to potentially study, and maybe at some point you can look UCD or something else. There is a third thing that this is related to, which I also mentioned, is that with a soft Gauss constraint, this is the toric code, and as the name suggests, the toric code is proposed as a means of topologically protected encoding of information, right? So it's a topological error correction code. So it has relevance to quantum information theory. And the fourth aspect of this very same model, which is relevant, is that this is, you can think of this as a very simple toy model for a quantum spin liquid. So quantum spin liquids are appearing first with magnetism, and it's essentially these are quantum paramagnets. So where usually when you have a paramagnet, you start from a ferromagnet, you heat it up, then at some point the fluctuations will become so strong that the system will become disordered. A quantum paramagnet is something where you start from an ordered state, and then you increase at 0 temperature, you increase a parameter in your Hamiltonian, which increases quantum fluctuations. And at some point, the quantum fluctuations become so strong that the system becomes quantum disordered. So we will see that if you interpret this Hamiltonian, this plus this, as a model for spins with a very weird 4-spin interaction, but still it's a local interaction of spins. You will see that this is the paramagnetic ground state that we find. In the sense it doesn't break any symmetry. In fact, quantum spin liquids are by now actually characterized by having strongly entangled ground states. That's what we will see. Okay. So there are these 4 phases of this medal with 4 phases. Okay. Now I promise to speak about the duality to the transfer speed disorder. Grammars. Lanier. Mapping. Fully using model. Okay. So what we do is, and now maybe, yeah, I need new pictures. I need multiple of those. So what we will do is we will define new variables. Maybe you remember, in the case of the 1D model, we had the sigmas living on the sides and the mu's living on the bonds. Now we do something slightly different, as of the 2-dimensional generalization of this. We define sigmas living on the plaquettes. So the sigma operators will live on the plaquettes. So, and for example, sigma z as this plaquette will be defined in terms of, how do I do this best? Let's take orange. Will be defined in terms of the original mu degrees of freedom as a string which goes vertically up, and this is the string of mu x. So it's again mu x. Just 1 second. Yes.
What is the index of sigma z?
It's R and then star. So the notation is R for vertices, B for bonds, R star or a square for a plaquette. So a site in the dual lattice.
This string goes up to the boundary.
Well, okay, so again, as before, this mapping is, I mean, I'm sweeping boundary conditions under the rug. So imagine it goes up to infinity and disappears. In fact, if you tried to do this with closed boundary conditions, the string ends somewhere and then you're hitting some extra subtleties. So yes, so I've maybe define it here. So sigma z, sigma x on a given plaquette is just given by b at this plaquette. So that's nothing but the product of b, r star, mu z, e. So that's just the operator that we had before. This is the green operator. And the sigma z at the given r star is given by the string b gamma r star mu x e. And this is the gamma r star. So we call this here gamma r star goes up vertically from r star. So it's a semi-infinite string, and of course this choice is completely arbitrary, but it's the choice that I took. Maybe you also remember that in the Grama-Swann duality in one dimension, we had a situation where the mapping was such that we had adjacent sigmas or adjacent views mapping to the x. So mu z was mapping on adjacent sides to sigma x, and then the other one was something which had a semi-infinite string. So here it's sort of the same thing, but the problem with the semi-infinite strings here is that it's not obvious which direction to take. So because the string is one dimension lower than the dimension of space in this case. Okay. So of course, what we have is sigma x, sigma z on r star. So if they are at two different plaquettes, they commute. And of course, the sigma z's and all the sigma x's commute, etc. But then there is an important one, which is the anticommutator of sigma x r star with sigma z r star prime is zero. Is zero. The anticommutator is zero when it's on the same side. So how do we see this? Maybe I draw again, just for reference, I draw in the plaquette operator again. The plaquette operator was mu z, mu z, mu z, mu z. Right? This is the same. So the plaquette operator is the same as the. It's the same as the sigma x on this plaquette. So clearly, this operator commutes with this operator. Even if this string here went down here, let's say we want to know the orange operator, but down here somewhere, then it crosses twice the plaquette, and because crossing twice, you get two minus signs, they commute with each other. So sigma z's and sigma x's at non-equal sides commute, or non-equal plaquettes commute. Clearly, the sigma z's with itself commute because these are only given of mu x's. Clearly, the sigma x's with themselves commute because they're only given by mu z's. Now, how about when this guy and this guy are on the same plaquette? That means that this orange line terminates here. Then this guy has one mu x and one mu z, which are sort of living on the same Hilbert space. And they anti-commute, so the whole thing anti-commutes. Well, now we can do that to rewrite the Hamiltonian. Yeah, so the Hamiltonian in this notation, and I will write it down first, and you will not be surprised to see that this is the transverse reducing model, given that this is my promise. And then I'll explain how to get there. So it's a sum of adjacent nearest neighbors, sigma z r star, sigma z r star prime, minus lambda, sum over all r, sigma x, so sigma x r star. Okay, so where does this come from? Well, the lambda term is just the sum of all brackets with the b's, but the b's are now called sigma x's. So obviously, this here is just the same as that, but it's clearly by construction. This guy here, there are two cases. If we have a vertical bond, if this guy is a vertical bond, you have sigma z at this side and sigma z at, so at this bracket and sigma z at this bracket. That's a term where we have the semi-infinite string ending here times the semi-infinite string ending here. The only thing that's left over is the mu x living here. So for vertical bonds, it's pretty obvious that sigma z is nothing but mu x at the given bond. So it's this sigma z and this sigma z, it's the mu x living on this bond. What's a little bit less obvious is to do sigma z, let's say, on adjacent brackets, horizontally. Because when I do it horizontally, then I have a semi-infinite string here, and one more semi-infinite string here. So how is this thing the same as that one?
Gaussian constraint.
Gaussian constraint. So what you do is, you first draw these two lines, maybe I do this explicitly. So how do I draw it? I draw explanation of easing interaction of, let's say, horizontal leading interaction. So, as I just said, let's say we take here and here. Maybe I need more vertical lines. So here we have we want to have sigma z between here and here. So then that's a product like so. So we have here this is what it is, right? Goes up to infinity. It's x, 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 x. But then let's use the Gaussian constraint. Gauss constraint. How many do I have here? 4 of those. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I act, so this were the two that I was interested in. And I act here with my Gauss constraint. When I do that, that's a product of mu x's. So it's x, 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 x that I act here. X squared is 1. So what I get, if I do a Gauss on this, I put here a letter G for Gauss. I will act with a Gauss here. Then I will get here an x. And then I will remove these two fellows. And we get here an x. And I get here an x. And here an x. X, 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 X. So essentially this was my original string. This is what I got after I've applied it to Gauss. And now I apply another Gauss here. So I do this again. So the original ones that we were interested in, I marked them again in red. And then we have, so I now apply Gauss here, so we have this guy stays, because there's nothing happening here. And here do x, 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 but these two x's go, these three x's go away. There's one more x staying here. So we have the x now here, and my string starts here. So and thereby I can sort of unzip this and pull it out to infinity. Okay?
X squared or mu z squared is equal to 1 by definition.
Yes, these are Pauli operators. I didn't say this. I should have said this. Mu Pauli. And mu with x. All right. So, yes.
By unzipping, do you mean that you apply the symmetry string of these?
Yeah, exactly. I apply a string of Gauss operators to get rid of these strings.
And then you have a single.
And then I would have just a single sigma x left over, which is exactly what I'm saying, namely that the sigma z interaction with adjacent horizontally spaced packets is the same as just taking the mu x in between of them. So what I did here is I reverse engineered, I showed, well, I first introduced this model, then I introduced this model, and now I showed that this model is equivalent to that one. It was trivial to see that this term is the same as the green there. It was also quite easy to see that if these sigma z's are vertically spaced, then it's the mu x. And in order to see that when sigma z's are horizontally spaced one from the other, that then it's the mu x in the bond between these two sigma z's. In order to see that, you have to do this repeated application of the Gauss constraint.
So we work if we set it equal to 1, or if we set it equal to 0.
Okay, so there are different theories. You can put q equals 1, and then there are also something, I remind myself what it's called. So there are gauge theories where you set it equal to -1. Effectively, what this means is you have one extra charge on each side. It's as if there was a background charge. Yeah, then of course, this particular procedure would not work. But anyways, I introduced the simplest Z2 gauge theory. So there are various gauge theories. You will actually see in the course of the lecture there are. So we will see later, we will not change this essentially. We will always say, even in the toric code, in the situation when H is positive for the course of the lecture. But we will see that when lambda changes sign from positive to negative, the b's, instead of being wanting to be +1 everywhere, they want to be -1. So that's actually the reality between the q's and the b's. We will actually get there in a second. And then you end up in a different topologically ordered phase. I will also explain in which sense this is a different topologically ordered phase. You can understand this again by representations of symmetries, relations, it has relationships to these projective representations. Okay. So what did we do? The goal was, I didn't show you yet that the toric code or the Z2 gauge theory has topologically ordered phases. But for the moment, let's believe it. And what I showed to you is that indeed, essentially the main thing that I wanted to show you so far is this. So, okay, so let's just believe that there will be topological phase in terms of mu's in the trivial phase, and I showed you that they are also related by a non-local transformation to usual symmetry breaking in terms of the easy model.
What is the value of J over lambda for the transition?
It's hard to calculate. Probably it's known numerically. So the reason is that, so this here, this is 2 + 1 dimensional transistor easing. So this here is a universality class of 3D easing. So this is a universality, You understand what I'm saying? Yeah. So therefore, this is it's not a simple field theory to study, and therefore also this, there are corrections to the transition, but it's order 1. Maybe since we already asked about transitions and gauge theories, there is one more subtlety that can appear. So so what you see here is that the transition out of the topologically ordered phase is essentially the same universality class as the easing transition. Right? This here is called the deconfined phase in terms of the gauge theory. This is called the confining phase. This deconfinement confinement quantum phase transition, as I just said, looks like an easing phase transition. However, gauge symmetry does not allow you to have all the operators in your critical theory. So it happens in the context of these gauge theories that the critical theory lacks some operators, even though it originally is the same as the easing gauge theory. So in this case, one would call it easing with an asterisk. Yes? Well, I didn't explain anything about it so far, and I will spend well, at least the rest of the lecture to have not heard of the next. Maybe, but let me just I use the word confinement and deconfinement. So I will explain the word topological order, but maybe it's in terms of this gauge. And well, I'll switch to the toric code essentially now. I will do the soft constraint. But to use the language of the gauge theory, the notion of confinement and deconfinement, well, you know it from QCD, right? So in QCD, you have the question whether essentially you can take two quarks and pull them apart, and and they live separate lives, yes or no? And quarks cannot do this because it's a non-abelian gauge group. And then you can ask, but then for abelian gauge groups, we know that in principle there are situations where you can pull excitations apart from each other. So essentially, this is the question we're asking here. You have a very simple abelian gauge group, just C2, and you can ask the question: can I pull excitations apart from each other at no cost, or does it cost something? Good. So let's now switch to solution of the toric code. Obviously, I'm introducing the toric code here as a Hamiltonian, and I look for its ground state. In reality, I mean, in reality, in the quantum chip, the reality of the quantum chip is that this state is being constructed maybe dynamically or something like this. Right? So by constant measuring of certain ancillary qubits or something like this. But
the lights follow four steps of gates in the software.
Say again?
That light there will 4 layers of gates construct very important.
Okay, so maybe I should say something. I mentioned, I'm not sure what you mean by construct, but of course I mentioned that it's impossible to construct a toric code ground state with a finite depth circuit. Right? That's the very definition of topological order. So you cannot just apply 4 steps of unitary gates. What you can do is either you apply a procedure, and this has been done in an experiment, I've shown this I think in the intro slide. Either you apply an infinite depth circuit in the sense that it scales with the width of the system. Or what you can also do is you can apply codes which are use measurements. So essentially, and then it's actually a very shallow circuit. You can do it in a very shallow circuit if you measure. So you prepare something, and then you measure projectively, and then you can correct for certain errors in a very shallow circuit. You can do this. But with unitary circuits, you cannot get to the toric code ground state in a finite width, depth. Okay, but anyways, I'm a state theorist, so I do Hamiltonians and looking for the ground states instead of doing something then. So as I said, so it's a ground state. So the main thing about it is what I said already before, but let me emphasize it again. All these Q's and all of these B's commute. So Q, R, P, delta equals 0 for all pairs of R. Second, I will now consider the situation where J equals 0. Then all the Q's, so the Hamiltonian that I'm looking at is this plus this, right? This is what's called the topological. But I'm taking J equals 0. So then it's only this plus this. And in this case, all QR and V delta are integrals of motion. That means they commute with the Hamiltonian. Well, I just said that all the Q's commute with all the B's, and if the Hamiltonian contains only Q's and B's, then obviously all of them commute with the Hamiltonian. The number of Q's and B's, so there is, on each unit cell, there is a Q and there is a B, right? So I can associate it to this side here, this Q and this B, which is to the northeast. And then, essentially what this means is that you have two of these Q's, two such integrals of motion per unit cell. You had two original degrees of freedom per unit cell. These Q's and B's, that's something that I did not say so far, I think. QR squares to 1, and B squares also to 1. That means that these guys here have a two-dimensional Hilbert space. So essentially what you have is the number of degrees of freedom is equal to the number of integrals of motion. Again, it's a statement modulo boundary conditions, but it's at least extensive. So the number of unit cells, the number of integrals of motion is linearly proportional to the number of unit cells. So for the moment, just think about you have as many integrals of motion as you have degrees of freedom. Then you can uniquely characterize each state characterized by the set of QRs and the set of B's. So I can write it like this. All the sets of QRs and the sets of B's. You can just diagonalize each thing by itself, right? And then you get the full quantum state. In particular, if lambda and h are both positive, the ground state is when all the B's are 1 and all the Q's are 1, right? So this constraint here, the fact that they square to 1, this implies that each of them are QR has eigenvalues plus and minus 1 and B delta has eigenvalues plus and minus 1. We can go into the eigenvalues of each of the QRs and each of the B's, and that's the status that we chose. Then the ground state equals all of the QRs are 1 and all of the P bucket are 1. Again, I'm using the word ground state as if there was a single one. We will see later that there are subtleties. Okay, so how do we do this? Let's construct such a state explicitly. So we have these two guys here. They do commute. Maybe it's useful to start to make, so essentially the goal is to make each of these terms separate, right? I mean, the problem falls into, there are infinitely many terms in this sum and infinitely many in this sum, but each of these terms has to be happy to be in the ground state. Happy meaning P equals 1 and Q equals 1. So let's start by making the B's happy, and then later we take care of the Q's. So each some space, I know a state which makes all the B's happy. state which makes all the b's happy. It's a state in which all of my qubits point out. This is a state which has 0 flux. You want to have b equals 1 that corresponds to 0 flux. Because it means you take the product of all the gate. I mean, remember this was a e to the I of the flux the thing, and so 0 flux is b equals 1. You agree this has 0 flux? It's a product of, I mean, this is the Z eigenvalues that I'm drawing here, and it's, okay, this plus 1 and plus 1 and plus 1 and plus 1 is 1. Of course, if the goal was to make only this guy happy, to have a configuration with 0 flux, there are of course extensively many such configurations you can do this. They are all related by gauge symmetry. So we also need to take care of this one. So we need to lift this degeneracy. And how will we do this? We take the state and we just on each side project it on each side. We project it with a QR equals 1 subspace. Actually, this is not the normalized ground state, I think, but we don't need to think about normalization.
Why is the flux equal 1 all points up? You're going to perceive 1 also 2 points up.
Absolutely. It is absolutely possible. That's what I tried to say before. There is not only one configuration which gives you b equals 1 everywhere. You can also have configurations where the only thing that you need to have is you need to have an even number of ups and an even number of downs, which is okay. But it is okay to start from this one. Do you agree this is a solution?
Yeah.
Okay. Now we will actually see that this guy here cycles through all the possible solutions. But let me emphasize again why this is the ground state. So we wanted to have a ground state. We want to see that when the Hamiltonian without the J, when this guy acts on this, then we get the minimal energy state. So if you act with an arbitrary Q on this state, well, this is just by definition, this is a vector, right? So when you act with the twin, you get Q plus Q squared, Q squared is constant. Obviously, you get Q plus 1 eigen, so this is an eigenstate. Q on this thing equals to this thing. When I act with the B on this, I act with B here, then I told you that the B, any B converts any Q. So I can just bring it across here. And then I act here. So B on this thing is this thing, which means that the eigenvalue is plus 1. Mission accomplished. Now your question. This here, as said before, this is a highly entangled state. And how do we see that? Maybe let's step back a moment and remember what's the paradigmatic example for entanglement. At least in my understanding, the paradigmatic example is the spin singlet of 2 spins. So up, down, minus down, up. Such a belt state has, it's not a product state, it's a superposition of 2 states. And this superposition has, in the case of the singlet, made out of 2 spins, it has as many terms in the superposition as there are degrees of freedom, namely 2. Up, down, minus down, up is 2 terms and 2 spins. This here is a superposition of product states. Only this is a product state, but we take a superposition of those. And there are as many terms in the sum. Well, next, what I want to say is there's an extensive number of terms in the sum. Why? Because what you have to do is you have to take the product of all of these guys. So when you expand this product, you get an extensive number of terms. So when you try to write this out explicitly, you will see that you get many, many terms. And I wanted to draw the first one of those for illustration. be drawing a lot of arrows. So the first one is just all arrows, right? So the second one is, let's start with putting arrows up, but then in this here in this product, there is a product where you have n minus 1 ones and 1 cube. Right? So let's say we have a cube which is acting on this side here. What does it do? When I have 1 cube acting on the state here, the cube is the product of mu x's that flips the spins. So we get this here. If the mu happens to act here, we get this. So down, down, down. Up, everywhere. Right? So what you have, a Q, what a Q does is a Q generates a closed loop of downs. If I act with another Q, let's say I act with a Q here, then I get a closed, so it's also the down. I get a, this guy will be flipped up again, but these three will be flipped down. Then I get a closed loop which is bigger. And then, and so on and so on and so on, right? So what we get in the end is a superposition of all these closed loops. Well, I don't know, all of these loops. So we have essentially a ground state which is a superposition of loops, and that sort of started this business of string net condensation as a means of constructing topologically ordered ground states. Yes?
But the factors with which each of these
Very good question. I mean, in this case, the prefactors are all 1. But in principle, you could have, for example, imagine I was going to impose q equals the event h is negative. So I want to q equals minus 1 everywhere. Then I do the same construction but with the minus sign here. And then I have a minus sign here, plus sign here, and the alternating phase. In this case, the phase is plus minus 1. And this is a different state of matter. So indeed, in the superposition stage, that's it's the same thing as for the spin triplet, as z equals 0, which is up, down, plus, down, up. And the singlet, which is up, down, minus, down, up. The sign between the two summons main methods. Okay.
Should be similar in which terms, like best vectors or Yangians.
Okay, I don't know what you're doing. Can you repeat what you said?
The features
Yeah.
look similar to best vectors.
Beta vector?
For, beta, like beta answers
Yeah.
for Yangians. Is it somehow
Okay, so I have no idea what you're speaking about, so I cannot comment.
Okay.
What are Yangians?
Yangians?
Yang what?
Okay, not really.
Alright, you tell me later. Okay, so. Okay, I think I said everything that I wanted to say. Let's switch to excitations. Yeah.
Please tell once again why those ground states are still ground states.
These are ground states?
Okay, yeah. Everyone.
Okay. You agree that when I act with, okay, so I explained it at the level of this one, but let's understand it at the level of this one. You agree that when I act with B on this, I get 1, in any case, because I have always an even number of ups and downs in each bucket. For construction, there's always an even number of ups and downs.
Oh,
So
okay.
B on this thing will leave each of the state invariant by itself, and you will get eigenvalue 1. If I act with a Q on this, then the terms in the sum will change order. For example, I act with a Q here, I will go from this to this, but this guy will become this, so they swap space. Yes. So this is really nothing but, as I said before, yeah, you're going through all the gauge configurations, cycling through all the gauge configurations. Okay, excitations. So I said that in any case, you can always characterize any state like this. The ground state is the one where all the q's and all the v's are 1. So excited states at lowest cost is to flip one q or one v. This is going to be a local excitation, so we call such local excitations above the ground state a particle. Okay, okay, so the simplest excitation is, for example, flipping a plaquette. And we call flipping a plaquette, remember that a plaquette term is nothing but a magnetic flux. So flipping this is called an M particle. So what this is essentially pictorially represented as product over R, 1 plus QR, and then, again, I omit all of the red arrows, I draw just the green lines, but it's an open line now, it comes from infinity and goes in the here. What's a green line? A green line is a semi-open string, which we call WM, ends at a certain position, a certain plaquette, and it's a product over how do I write best? Right, inverse. There B along Boole lattice. And then we have here uxt. Like so. And it ends at this particular okay. There's a product of mu x here, mu x here, mu x here, mu x here. Essentially what this is nothing but nothing but Wm on this zeros, this is a zeros packet on the ground. You see that, so what I do is to create this excited state, I act with a semi-infinite line, and since the mu x is commutative to R, if I act here, I can bring it through and will do nothing but this, which a green line, as you remember, is flipping all the spins from up to down. So if everything before was up, now there is down, down, but this doesn't change the value of B here. Down, down, that doesn't change the value here. Down, down, doesn't change the value here. This is still B equals 1. But here I flipped only one spin. So now I flipped at this position, I flipped the magnetic eigenstate, the B, from +1 to -1. So this guy has energy above the ground state, so counted from the ground state, it has energy, what is it? 2 lambda. You had a question or you want to ask a question?
What M means?
What?
What M means?
M means M particle for a magnetic particle. So we will have M particles and E particles for electron particles.
So this is a state with some specific role, or this is already assumed. Is this a state with a specific role, or this is just a state with the superposition of each possible role semi-infinity?
So this guy here has the superposition of all of these loops.
Okay.
This here, without the line, is the superposition of all the loops. But given that the line, this W, commutes with the 1 plus Q, I can just bring it across. So here is a specific configuration. So everywhere where you don't see the green line is spin up. And only where the green line is spin up.
Why is it another to lambda?
That's above the ground state, so maybe to do that.
Yeah, why is it repeat the
Because the energy of the ground state is all the B's are +1, so it's minus lambda times the number of sides. When I flip one side,
why one?
This is my simplest excitation that I can have.
Yeah, I mean,
Flipping
why
two got more energy.
switch correspond to the only one? Why does the switch correspond to the
It
only
only
one?
flips this guy. This here is not flipped because I flipped 2. Flipping 2 spins doesn't flip the B. But here it's only here 1. So, yeah. Now there is something which is the analog to this. It's flipping one of these Q's. So that costs, of course, that only exists in the toric code limit, but doesn't exist with the H infinity. It costs 2H. It's called the E particle, and lives at a given position in the lattice. Let's call it R0. That one is a little bit harder to draw. So actually, I'll draw it just simply as a line. So you can still, okay, maybe let me emphasize. There is this duality that I have briefly spoken about. I decided to draw everything in terms of the E basis originally and then act with the Q's. I could have done otherwise. I could have taken the X basis, and I could have drawn in the X basis the starting state, which is, let's say, right, and then projected 1 plus B. There's complete duality between E's and M's. E and M's. It's not so convenient to write the string on the level of this thing here, if I write it for the E particle, but I can write it like so. WE on the ground state terminates at R0. And it's sort of the dual thing to this one. So the WE, I can represent it on the level of, well, I just represent it on the level of the lattice. As so. So this one goes along the actual lattice. And let's say it's here, it's ending here. And remember that this here was a product of x's, x, 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 x. This is the product of z's, z, 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 z. Okay? And yeah, so I write a lot of them formulas. So and it's orange, so let's do an orange. W R0 E is product of these along lattice. So not the dual lattice. So it goes along the lattice. This one went across the lattice, so from dual lattice side to dual lattice side. Times U Z B and ends at R0. Okay? Yes. You cannot. You say you cannot see this. Is that what you're saying?
I don't see what is the pattern for constructing this string.
So this is just a string that I'm drawing. This is not the state. And the string is a semi-infinite line of these. This line follows the actual lattice.
But just anywhere.
Oh, it can be anywhere. This is a very good question. I chose some line in my pictures, but it doesn't matter which one I take. And the reason is, and maybe that's a bit clearer here. Imagine I took a different line and I act on this thing. But this here, anyway, cycles through all positions. So if I act with a Q here, for example, on this side, my line will look not so, but will look like this. It will have the king one earlier. So anyways, given that I cycle through all of the gauge configurations, the choice of the line doesn't matter.
So it's not degenerate? Oh,
No, it just does not. So
I mean, this excited state is not degenerate.
it's not degenerate. There's only one state. Because as I said, the quantum numbers of the problem are the Q's and B's. We flip one B, so then it's the next station.
The king is also that doesn't
That doesn't know you can just look for a straight line. Okay. What else did I want to say? So that's the E particle because it sort of flips the electric part of the. This is the Gauss constraint, so you think about divergence of electric field density. You know, you flip this, so you have essentially changed your charge, the background charge. Yes.
I have a question regarding this, the toric configuration. Does it mean periodic configuration?
Very good. So I didn't get there yet. So far, I completely swept this under the rug. We will see that in the torus there will be more than one ground state.
But also in terms of like, what does the semi-infinite line in the torus?
Yeah, it doesn't mean anything. That's why I didn't say anything about it. It's not semi-infinite. So what this means is that when you have periodic boundary conditions, you cannot create a single of these E's. You can create an E and another, or an M and another M. And in fact, this sort of the notion of deconfinement in this case means that you can pull them apart without any string tension. I mean, it doesn't cost you energy. In this extreme limit, there is zero string tension. And then you can actually ask the question, how does it scale with this? Okay, so now I wanted to speak about fusion rules, and ideally I also wanted to speak about exchange statistics. Let's see if we get there. So fusion rules of the excitations. So remember what you know from, and I got kindly recollected, I got kindly, you guys reminded me how it works for spins. Imagine I have two spins, and I want to, I have two spins. I don't know much about this problem. I just know that this problem has spin rotation symmetry, and I know that in principle, microscopically, there are two spins, but then I zoom out, and I want to look at the system from very far apart. I know the system has two spins in it. I know it has spin rotation variant, so I know that there is a singlet and a triplet state. Right? So we know that essentially, if we take two spin 1/2 and bring them close to each other, the whole system behaves like either a singlet or a triplet. And we write this as, this is a reminder, we write this like so. I don't know how you write it, but maybe like so. And that's what it is. You can think about that two spin 1/2 have fused into a singlet or as a triplet. Now I'm discussing the fusion of these guys here. How do they behave? Fusion rules as effective objects. So if I have an M and I bring another M next to it and I bring it exactly on top, what do I get? I get a closed loop, which means that there is no M anymore. So I can bring M close to M, and once I've done that, I get nothing. I get my ground state. I call that 1. Close to means, imagine I have an excitation here, I have an excitation here, and now I do a sequence of operations which extend this string here up until it will reach this point. It's physically bringing one. So these excitations is at a point I.
So you connect.
Well, I bring them on top of each other. No, I can drag one to the next one and put them on top of each other. It's really, when I say bringing next to each other, I really mean this. I really, you can imagine that I have full access on of my sort of all of quantum states here, and I can change, I can flip through this one by one, and thereby extend what my operation is. This is actually what they do. In the first talk, I show you this picture on the statistics and what they do for the toric code excitations. That's what they do on the chip.
Like without overlap.
Without
We bring them close to each other without overlap.
here, to illustrate it, imagine you have overlap. So we're really bringing them to the exactly same point.
But no more overlap.
Well, you cannot have more overlap than being on the same point. Right?
I mean, this is not out.
Exactly. That's the point. So once you have brought this guy here on top of this guy, since it doesn't matter which string I take, I have two strings on top of each other. Each of these W's is square unity. So that means there is nothing. This is what this rule means. So what I'm saying is, I would say mathematically rather easy. It has some deep consequences. But I think you in your head take it right. You bring two of these m's next to each other, and then it's done. It's nothing's there, and that's what this symbols mean. Yeah. And you can do the same thing when you bring an E across to an E. You bring them on top of each other, like that. Then you can ask the question, okay, so you can ask, there is in the fusion rules, people also discuss what happens when you try to fuse E with 1, but that's sort of trivially E. Then there is a third non-trivial one, which is, what happens if I try to bring one of those guys close to one of those guys? So I bring here my E particle. Remember the E particle is on the vertex and the M particle is on the bucket. Imagine how you build a molecule of these guys here. What's this object? Is this nothing? And the answer is no. It's not nothing, and we don't know what it is, and we have to give it a name. And actually I forgot whether I called it epsilon or something else in my notes. Yes, I called it epsilon. So this is something new. You could imagine that essentially you have some additional interactions and you form this bound state. So that maybe like in an exciton, creating an E by itself, because the energy of E and M is higher than the bound state. You know, separate, like in an exciton.
The equivalent of some products of M of different directions. So it's not group that is not.
What is the which one is the product? Last one. No, it's not a product of M, because it also includes these guys here. This guy has an electric charge. So it cannot be just a product of M.
Charge and the monopole, that's why M.
Yeah, well, I mean, yeah. I would call it the Bison or so. But you can also subtoning is the monopole. M really stands, I think it stands for magnetic, because E is, how do you want to construct the word with E other than electric?
E is a charge, yeah, an electron, and M is a monopole.
Okay, so that's okay. So within this model, simplest model, the energy of epsilon is just the energy of E and M. So it's 2 lambda plus. Yeah. But in principle, you could imagine some interactions which reduce this, so that the bound state is lower in energy than the excitation of the two separate. So then eventually you create one here, and then one together. And then you can ask the question about this object as an excitation by itself.
What kind of direction? Then I have to the different direction.
Yeah, external.
What is not close enough for E? Close enough for E, which is low.
Okay, so I mean, imagine you just have, okay, let me just draw on top of this a string for M. The simplest situation would be this. Then you have here your M and here your E, and they're just next to each other. Yeah. Okay, obviously I'm out of time.
Then
Yes.
apparently there is this several kinds of epsilon depending on relative positions.
Right, and you can ask the question whether they can sort of square, it's like a molecule, right? This will not be of relevance here, but in principle you can ask this question.
Is the relative energy different or is different kinds of epsilon?
That's the question that depends on the exciton you want to write it down.
For this one,
So yeah, for this Hamiltonian, the energy is anyways not lower, right? It doesn't necessarily want to do bounce this. Okay. We continue tomorrow.
That's the speaker.